Prospectus. The purpose of this book is to introduce the reader to the notion of a topos and to explain what its implications are for logic and the foundations of mathematics. The study of topoi arises within category theory, itself a relatively new branch of mathematical inquiry. One of the primary perspectives offered by category theory is that the concept of arrow, abstracted from that of function or mapping, may be used instead of the set membership relation as the basic building block for developing mathematical constructions and expressing properties of mathematical entities. Instead of defining properties of a collection by reference to its members, i.e., internal structure, one can proceed by reference to its external relationships with other collections. The links between collections are provided by functions, and the axioms for a category derive from the properties of functions under composition. A category may be thought of in the first instance as a universe for a particular kind of mathematical discourse. Such a universe is determined by specifying a certain kind of object and a certain kind of arrow that links between different objects. Thus, the study of topology takes place in a universe of discourse category within topological spaces as the objects and continuous functions as the arrows. Linear algebra is set in the category whose arrows are linear transformations between vector spaces, the objects. Group theory in the category whose arrows are group homomorphisms, differential geometry where the arrows are smooth maps of manifolds, and so on. We may thus regard the broad mathematical spectrum as being blocked out in a number of subject matters or categories, a useful way of lending coherence and unity to an ever-proliferating and diversifying discipline. Category theory provides the language for dealing with these domains and for developing methods of passing from one to the other. The subject was initiated in the early 1940s by Samuel Eilenberg and Saunders MacLean. Its origins lie in algebraic topology, where constructions are developed that connect the domain of topology with that of algebra, specifically group theory. The study of categories has rapidly become, however, an abstract discipline in its own right, and now constitutes a substantial branch of pure mathematics. But further than this, it has a considerable impact on the conceptual basis of mathematics and the language of mathematical practice. It provides an elegant and powerful means of expressing relationships across wide areas of mathematics, and a range of tools that seem to be becoming more and more a part of the mathematician's stock in trade. New light is shed on existing theories by recasting them in arrow-theoretic terms. Witness the recent unifications of computation and control theories described in Mainz 75. However, category theory has succeeded in identifying and explicating a number of extremely fundamental and powerful mathematical ideas: universal property, adjointness. And now, a mere 30 years later, it offers a new theoretical framework for mathematics itself. The most general universe of current mathematical discourse is the category known as set, whose objects are the sets, and whose arrows are the set functions. Here the fundamental mathematical concepts, number functions, relations, are given formal descriptions, and the specification of axioms legislating about the properties of sets lead to a so-called foundation of mathematics. The basic set theoretic operations and attributes, empty set, intersection, product set, surjective function, e.g., can be described by reference to the arrows in set, and these descriptions interpreted in any category. However, the category axioms are weak, in the sense that they hold in contexts that differ wildly from the initial examples cited above. In such contexts, the interpretations of set theoretic notions can behave quite differently to their counterparts in set. So the question arises as to when this situation is avoided, i.e., when does a category look and behave like set? A vague answer is when it is at least a topos. This then gives our first indication of what a topos is. It is a category whose structure is sufficiently like set, that in it the interpretations of basic set theoretical constructions behave much as they do in set itself. The word topos, place or site in Greek, was originally used by Alexander Grothendieck in the context of algebraic geometry. Here there is a notion called a sheaf over a topological space. The collection of sheaves over a topological space form a category. Grothendieck and his colleagues extended this construction by replacing the topological space by a more general categorial structure. The resulting generalized notion of a category of sheaves was given the name topos. Independently of this, William Levere tackled the question as to what conditions a category must satisfy in order to be essentially the same as set. His first answer was published in 1964. A shortcoming of this work was that one of the conditions was set theoretic in nature. Since the aim was to categorially axiomatize set theory, i.e., to produce set theory out of category theory, the result was not satisfactory, in that it made use of set theory from the outset. In 1969, Levere, in conjunction with Miles Tierney, began to study of categories having a special kind of arrow called a sub-object classifier. Briefly, this is an embodiment of the correspondence between subsets and characteristic functions in set. This notion proved to be, in Levere's words, the principal struggle. The key to the earlier problem, he discovered that the Grothendieck topoi all had sub-object classifiers, and so took over the name. The outcome is the abstract axiomatic concept of an elementary topos, formulated entirely in the basic language of categories and independently of set theory. Subsequently, William Mitchell and Julian Cole produced a full and detailed answer to the above question by identifying the elementary topoi that are equivalent to set. As mentioned earlier, set theory provides a general conceptual framework for mathematics. Now, since category theory, though the notion of topos has succeeded in axiomatizing set theory, the outcome is an entirely new categorial foundation of mathematics. The category theorist's attitude that function rather than set membership can be seen as the fundamental mathematical concept has been entirely vindicated. The preeminent role of set theory in contemporary mathematics is suddenly challenged. A revolution has occurred in the history of mathematical ideas, albeit a peaceful one, that will undoubtedly influence the direction of the path to the future. The notion of topos has great unifying power. It encompasses set as well as the Grothendieck categories of sheaves, and so brings together the domains of set theory and algebraic geometry. But it also has ramifications for another area of rational inquiry, namely logic. The study of the canons of deductive reasoning. The principles of classical logic are represented in set by operations on a certain set, the two-element Boolean algebra. Each topos has an analog of this algebra, and so one can say that each topos carries its own logical calculus. It turns out that this calculus may differ from classical logic, and in general, the logic principles that hold in a topos are those of intuitionistic logic. Now, intuitionism is a constructivist philosophy about the nature of mathematical entities and the meaning and validity of mathematical statements. It has nothing to do per se with logic in a topos, since the latter arises from a reformulation in categorial language of the set theoretical account of classical logic. And yet we have this remarkable discovery that the two enterprises lead to the same logical structure. An inkling of how this can be comes on reflection that there is a well-known link between intuitionistic logic and topology, and that sheaves are initially topological entities. Furthermore, the set theoretical modeling of intuitionistic logic due to Saul Kripke can be used to construct topoi in which logic are generalized from set, turns out to be a reformulation of Kripke's semantic theory. Moreover, these topoi of Kripke models can be construed as categories of sheaves. These developments have yielded significant insights and new perspectives concerning the nature of sets and the connection between intuitionistic and classical logic. For example, one property enjoyed by the arrows in set is extensionality. A function is uniquely determined by the values it gives to its arguments. Now, the individuals of a topos may be thought of as generalized sets and functions that may well be non-extensional. Interestingly, the imposition of extensionality proves to be one way of ensuring that the topos logic is classical. Another way, equally revealing, is to invoke in arrow language the axiom of choice. Our aim, then, is to present the details of the theory just sketched. The currently available literature on Topoi takes the form of graduate-level lecture notes, research papers, and theses wherein the mathematical sophisticate will find his needs adequately served. The present work, on the other hand, is an attempt at a fully introductory exposition aimed at a wide audience. The author shares the view that the emergence of Topos theory is an event of supreme importance that has major implications for the advancements of conceptual understanding as well as technical knowledge in mathematics. It should therefore be made available to the philosopher-logician as well as the mathematician. Hence, there are very few prerequisites for this book. Everything, set theory, logic, and category theory, begins at square one. Although some material may be very familiar, it should be remembered that one of our main themes is the development of new perspectives for familiar concepts. Hence, it would seem quite appropriate that these concepts be reappraised and that explicit discussion be provided of things that to many will have become second nature. There are a number of proofs of theorems whose length and detail may be discouraging. A similar comment applies to the verification of the structural properties of some of the more complex categories, sheaves, Kripke models. The reader is recommended to skip over all of this detail initially and concentrate on the flow of ideas. It can often happen that although the verifications are long and tedious, the facts and ideas are themselves clear and readily comprehensible. Hopefully, by steering a judiciously chosen course through elementary expositions that will bore the cognizant, abstruse constructions that will tax the novice, and detailed justifications that will exhaust anyone, the reader will emerge with some insight into what and why of this fascinating new area of logical mathematical philosophical study.